We're going to talk about graphing sine and cosine now. We've the progression of the course so far has been learning a lot about the unit circle, which is depicted right here. And as we've talked about a lot in those videos, we're going to relate everything to the unit circle in trigonometry, and that's especially true with graphing. So we're going to focus on graphing sine and cosine, but if we understand that, extending it to other trig functions is really not a big deal. What I'm going to do is I'm going to start out by, again, relating everything to the unit circle. We're going to look at the graph of sine, and then right below it, we'll look at the graph of cosine. We're going to relate that entire thing to the unit circle. And then we're going to have a little activity that's going to be run through Desmos, where you can explore and link how these trig functions link back to past materials on function transformations. And we'll talk about manipulating these graphs and doing function transformations just like we had done previously in the previous section. Okay, so first, let's focus on sine and cosine and just think about their graphs and what they look like, the base functions, so to speak, as they pertain to the unit circle. So we're thinking about sine and cosine here, right? And so the first thing we're going to learn here is that sine and cosines are periodic, and they have period 2 pi. So there's two things we should learn about this in terms of what that means. Let's talk about what period means. So the word period in mathematics, or something that's periodic, means something that repeats, right? If something's periodic, it repeats itself. So when we say something is period 2 pi, that means it takes 2 pi units to repeat. And we know that the unit circle is 2 pi distance, right? And so a period is how long it takes a graph to repeat itself, right? Something's periodic, it repeats. And so the period of a graph is how long it takes to repeat. So 2 pi units in this case, because the unit circle is 2 pi all the way around, right? We should definitely have that in our brain by now. And so but I do want to just write it here. It's helpful to just write this stuff down so when you're reading this later, you say, oh yeah, that's why that's true. So anyway, since the unit circle has circumference 2 pi, that means that the x comma y values on the unit circle repeat themselves every 2 pi units. And let me be more specific. It's not units, it's 2 pi radians. Right, 2 pi radians all the way around. Or we know that as 360 degrees if we want to talk about it in degrees. Right? And so sine is the y value on the unit circle. Cosine is the x value on the unit circle. And since those values are going to repeat themselves every time we go around, in other words, every 2 pi, that's why these graphs have period 2 pi. And so as we start to dissect this first graph, which we can see is the graph of sine, right, we're going to look at sine first. And we know that from trig functions, the trig functions section, that when we think about sine at a specific t value, we're thinking about that as being a y value on the unit circle. Right, that's how we actually evaluate trig functions, is we would look for the y value if we're talking about sine and write down that value. And so if this is the unit circle, we can see that the sine is going to be the y value, and this graph is the graph of sine, is actually just the graph of sine tracing out the y values on the unit circle. Okay, so the first thing you should realize is this is 1 unit of sine. It keeps going. Okay, it keeps going in both directions. This right here between 0 and 2 pi is 1 period of sine. Right, that's why it takes 2 pi units. Okay, so again, let's relate it to the unit circle. And let's trace out the y values around this unit circle, right? So this is we're going to think about x comma y's as we go around here and focus on the y's because that's sine. And so the first thing that happened with the y values at this point here, this is the initial point, 1 comma 0, right? And so the y value here is 0. That's why this graph starts at 0. But then as we trace out the first quarter of the unit circle here, the y value goes from 0 and it goes up to 1, right? So this right here is the point 0 comma 1. And so that's why this first piece of the graph starts at 0 and goes up to 1. Okay, this is the point y equals 1 right here. Okay, so I'm just going to sort of mark, I'm going to do like little circles here, little squigglies. This increase in y values along those squigglies is this increase in y values along this graph. Right, see how they correspond to those things because we're tracing out the y values. Now the next part, notice, is marked right here. This next quarter is marking out this quarter of the graph, right? So the y values go from 0, 1, but then they drop back down to -1, 0. Right? So this point right here is -1, 0 on the unit circle. And so these ones are going down, these ones are going down. Right? So I'm going to mark these with x's. These x's that I'm drawing right here, see how the y values are going down? Those correspond to these x's over here. Right? These outputs are going down because they're the y values on the unit circle. And so this top half is sort of going up and down, is this part going up and down, right? Because we're tracing out the t values on the x-axis and the output values on the y-axis. And then the bottom half of the graph is going to follow very similarly. Right, so again, if we're tracing out the y values, here we are right in the middle. We've already traced out the first half. This is halfway between 0 and 2 pi, so this is pi. And we knew this was pi, right? If you go halfway around the unit circle, this is the point t equals pi. Right, we're just relating everything back to the unit circle. And so this next piece where it goes negative right here is the graph going negative right here. And so maybe I'll just do circles on this. So these circles that are going down, we're thinking about the x values, are these circles going down. Right, so we're tracing out that quarter, going down to -1. So this point right here is -1, right? I forgot to write that here. This point is the point 0, -1. So we're tracing out the x value, the y values. And then the final part, which I'll do in red, maybe just like with these. This is the y values going back up to 0. So from -1 to 0 is this piece of the graph. So this red squiggly corresponds to that red squiggly. Right, so if we're tracing out the y values on the unit circle, we just went around one time. Those trace out this graph, and this is the graph of sine. This is just one period. Right? It took us 2 pi to go all the way around the circle, and it just continues. Right? The next 2 pi would just trace out the same y values again. We could also go the other direction. It's just tracing out the y values in the other direction. Right? So anytime we're thinking about sine, we're thinking about the y values on the unit circle. I'd like to just kind of drive this home a little bit and clarify it further by thinking about exactly what happened with one period of sine. Okay, I'm going to try to, maybe I'll just squeeze that in right next to it here. So in one period of sine, right, we had our max and our min took place at plus or minus 1, because those are the biggest y values on the unit circle. To dissect it further, the max happened, right, the biggest happened right here. That point is right here on the unit circle. That happens when t is pi over 2. And so if we are more specifically, the max occurred at t equals pi over 2 because y equals 1 there. And the min happened right here. That's down at the bottom of the unit circle. That's at the point t equals 3 pi over 2. Right, so if we're thinking about the minimum value, it was at 3 pi over 2. Should be a 2, excuse me. And that's because the y value is -1 there. The places where it crossed, right? So we like to think about x-intercepts, or in this case, it's kind of like t-intercepts. This initial point where it crossed, this point in the middle where it crossed, this end point, are all the places where the output is 0. Right? So those are going to be the places where the y value is 0. So it happened here at the start, it happened halfway through at pi, and then it happened again at the end at 2 pi. And so when we're thinking about the x-intercepts, or the t-intercepts, those happened at t equals 0, pi, and 2 pi. Right? So it's helpful to think about the sort of the characteristic of the base graphs, right? So again, we're thinking about y values on the unit circle for all of these facts. We can just relate everything back to the unit circle. We don't have to think too hard. We don't have to memorize this stuff. We can just understand it, right? We can always recreate this graph just by thinking about the y values on the unit circle. Let me know if you need some more help with the unit circle. I did try to emphasize that a lot when we were first learning the unit circle, and it's really important. So let me know if you need another review of that. Okay, so this is just, again, tracing the y values out creates this graph. Now this lower graph here is just sort of the same exact graph, just continued. Okay, so in other words, this is between 0 and 2 pi right here, right? On the first graph. Here's 0, here's 2 pi. So this graph right here, between these two places, is exactly what we just sort of did, right? So it's just like a shrunken down version of that cutout piece. This is, again, the same graph, right? So this is sine here. It's the same graph we can see. Kind of has the top bump and the bottom bump. And it's just tracing out the values on the unit circle that those occur. Okay. Now cosine works the exact same way. I'm not going to go through it in the same amount of detail because it's the exact same thing, but we can do it in a similar kind of way here. So this is now cosine. Make this clear here. So now we're thinking about cosine of t. And when we're thinking about cosine, we're thinking about the x values on the unit circle. Right, so for sine, we were thinking about the y values. Now we're thinking about the x values. That's sort of the key difference here in cosine. And so that's what gives it a different shape, right? Sine had this wavy kind of shape because it was tracing the y values out. But when we trace the x values out, it makes this bowl-shaped kind of thing. And so let's just go through that quickly to hopefully make it clear in our heads. And let me just draw a mini unit circle right here so we can kind of trace it out as we go. This is our unit circle. We know we always start right here. That's the point 0. T equals 0. And it's the point 1, 0. Right? So the x value actually starts at 1 when we're thinking about the unit circle. And so that's why the graph of cosine starts at 1. Right? Because if we're starting with the output, the x value starts up at 1. When we trace out the unit circle going this way, this next point is the point 0, 1. And so the x value, right, again, we're thinking about the x values here. The x value went from 1 to 0. And so that's why this went from 1 to 0, right? So the first quarter right here is tracing out the x values. When we keep going, the next point right here is minus 1, 0. And so if we're thinking about the x value, it went down to minus 1. So that's why this next piece goes down to minus 1. Right, so this first half of the graph of cosine, right, just to be clear, this is cosine. We're tracing out the x value on the unit circle. It went from 1 to 0 to minus 1. 1 to 0 to minus 1. And then the second half just does the opposite, right? The x values go down here. This is 0, negative 1. So the x values go back to 0. And then, of course, they go back to 1. And so when we're tracing out this second half, this is the x values going from minus 1 to 0 to 1. Minus 1 to 0 to 1. And so this is one period of cosine then, right? Inside this box that I'm kind of drawing right here is one period of cosine, right? It's that bowl-shaped kind of thing. Starts at 0, goes to 2 pi, just like sine does. Right? They have the same period, they just have different shapes. And it repeats. So this is one period, this is another period, and it kind of keeps going, right? It would keep going this way, etc. Cool. Okay. I do want to just summarize too what we were thinking in terms of the maxes and the mins and stuff. It's nice to write this down. You might want to pause the video if you haven't written that down already. This sort of traced out what we were doing with sine. I'd like to write the same thing down right here, and we can reference the graph right above it for one period of cosine. So we're tracing out the x values. The x values, again, had a max at 1 and a min at minus 1. They just happen at different places, right? So the max happened right when we started, right at the start of the graph, right? And so we had our max and min at plus or minus 1 again. Except the max happened at the start and the end. And again, that's because we're tracing out the x values. And so that's where the x values were 1. If you want to know where the x values are the smallest, they're the smallest over here on the left side of the circle, right? So that happened at halfway through at pi. So the min happened at the bottom of the bowl, was right in the middle, because that's where the x value is -1. The places it crossed, those two places right there where it crosses the axis, that's where the x value is 0, right? The x value is 0 at those two places. And so that happens at pi over 2 and 3 pi over 2. We have intercepts at 3 pi over 2, and I forgot n pi over 2. So I hope that just, that helps you think about where do these shapes come from? These are the base functions. How do we get those shapes? And what we're going to sort of move on to in the next part is manipulating those shapes, thinking about how do we change the shapes? How do we stretch it? How do we shrink it? How do we move it up and down? And it's all related to stuff we've learned already. Okay. Before I do that, what I'd like to do is I'm going to share my screen and show you the activity we're going to work on in a second. But the first thing I'd like to do is just show you where the stuff gets used. Just sort of take 1 second and give you a little preview about where you might actually see trig functions show up in the real world. And so we use trig functions all the time. And I'm just going to give you a couple examples of where. Sharing my screen here. Okay. So the first thing that we sometimes use trig functions for are plotting the relationship between predators and prey. And so here's a predator-prey relationship being plotted. And you can see we're plotting rabbits and foxes, right? And we have time on the x-axis. This is like months down here, right? And this is number, this is population on the y-axis. And so something that happens with rabbits and foxes or any kind of predator-prey is they have an impact on each other. So for example, if there's some amount of rabbits right here, like we're starting with some amount of rabbits, they're going to get eaten by foxes, and so the population might go down. Right? So the rabbit population in this first piece, let me just highlight this first part of the graph. The rabbit population is going down there. In response to the rabbit population going down, the foxes are also going down, right? Because they're running out of food. And so you can see as the fox population extends, it continues to go down because they're running out of food. Well, now there's not as many predators around, and so in the same piece, towards the end, the rabbit population is starting to go up again. And so the rabbit is going up because there's not as many foxes eating them. Excuse me. Now that the rabbit population has gone up in this piece, because they're not getting eaten, there's more food for the foxes, and so the foxes start to go up in this piece. Oh, now that there's more foxes, they eat the rabbits, and so the rabbits start to go down again. As the rabbits go down, there's not enough food for the foxes, and so the foxes will go down. So you can see there's this, what's called a feedback or a dependence on each other where one impacts the other. And so both of these curves look like sine cosine curves, and we can model them using sines and cosines. So that's one sort of application that we often see is this feedback and predator-prey relationship where we can use sines and cosines to depict that. It also happens very obviously and commonly in like sunrise, sunset data. So as the sun goes up, the moon goes down kind of thing. Obviously, it depends on the Earth turning. But as we plot the time at which that happens on a given day, as the sun goes around the Earth goes around the sun, we get sine and cosine curves that we can also plot and model using sines and cosines. It's also very highly applicable in physics in general, and specifically measuring visible light and things like X-rays and radio waves and things like that. right? And so for example, we're only able to see certain things that are in a certain wavelength. And when someone says that, that means that light and other things that move through the air without us seeing it create sine and cosine waves, right? So that's what's being sort of depicted right here. It shows the relative size of different types of waves. Right, so things like X-rays, if you broke a bone or something, have very tight kind of sine and cosine waves compared to radio waves, which are longer. And the longer a wave is, sort of the further it'll travel. And so that's why radio waves are very long, so you can pick them up in your car from a distance, whereas X-rays are very short, so that it can sort of penetrate your skin and look at your bone from a short distance. Right? But you wouldn't expect to be able to take an X-ray of someone from very far. And you can see in all this spectrum of different waves, we're actually only able to see visible light. And so visible light in the middle here is a very, very narrow spectrum of the overall potential size of different waves. Right? So we're only able to see very, very specific size of things, which is why we're not able to see X-rays and radio waves and things like that. But the interesting thing is those things could be all around us at all times. I mean, we could turn on a radio in pretty much anywhere in the world, or at least in the United States for sure, and pick up some radio station, right? An AM station. They have really long radio waves that travel really far. So that means there's just radio waves around us right now making sines and cosine shapes that we can pick up with a radio. Kind of cool. Just to kind of look into sort of deeper applications in say Fourier series or other Fourier transformation, kind of similar things. Those are using sines and cosines to represent other things in our world. So you can use sines and cosines to compress a picture. Like if you sent a picture over the internet or a video or something like that, you can compress that image to make it smaller using sines and cosines to represent those images or music or something like that. I know that's very vague, but this just sort of just shows the general idea where you can mimic the shape of various things, again, like music, or for example, using sines and cosines. So it really does come up quite a bit. And the deeper you get into mathematics, or the more you see sines and cosines. It's often why people want you to take this course. Okay, so there's an activity now. I guess let me stop sharing my screen for 1 second to preview the activity on the next page. We're going to explore these sines and cosine shapes using transformations. And so we're thinking about sine and cosine, but we're going to be looking at them in a more general sense using function transformations like we had previously. Give me 1 second just to get my notes set up. Okay. So here's a sine function and a cosine function that have been transformed, okay, using the various transformations that we had seen in past sections. So before we dissect this sine and this cosine function, let's look at the potential transformations that are going on in those things. So the first thing, these 6 things right here we had talked about previously, right? In other words, I think if you look at approximately page 22 in our notes on function transformations, you'll see this information, right? And so given a function f of x, you can do these transformations to those things. These 3 things on the left are changing the y values. Right? These things on the right change the x values. So we're going to get into what exactly they do. Let's just make that clear. How do we know that the things on the left are x value or y values and the things on the right are x values? Well, notice the formation here. This is f of x plus c, where this is f of x plus c. Right? And so the difference there is that this is the output, and then you're adding a number, and this is adding the number directly to the x values. Right? So everything in the right-hand column is directly impacting x values, where everything in the left-hand column is impacting y values. The dog just came in, opened the door. Give me 1 second. And so what we want to do, maybe while I'm going and shutting my door, think about how these 6 things are being represented in that function right there. Okay. So as a quick reminder, when you take a function and add a number, it's a vertical shift, right? And so adding these plus c's on the end is taking the function sine or cosine and adding a number to it. And so we've got this plus c doing the plus c here. Vertical stretching or shrinking is multiplying the function by a number. And so up here, the thing multiplying would be the a on the outside, right? So sine is the regular function, and we're multiplying it by a number. And so the second a here is the vertical stretch or shrink, depending on what it is. And then we also learned that if we plug this c right here, if this c right here is negative, it'll flip the graph vertically. So those are all the vertical transformations that are going on in this particular function. The horizontal transformations are the ones that are messing around with the x values, right? So if we take an x value and add it or subtract it from the, or add or subtract a number from the x value, excuse me, that looks like b potentially, right? B is the one that's being subtracted from the x. And so this b right here, or this b right here, is a transformation that corresponds to this, horizontal shifting. Horizontal stretching or shrinking is multiplying the x value by a number. And so what's multiplying the x value up here? That's the k. Right? The k is the thing that's multiplying the x in both of those, and so that's doing a horizontal stretching or shrinking. And of course, what we also know is we can flip horizontally if that c is negative, right? So this k is going to be in charge of horizontal flipping as well. So the first thing you should do, and the way, I'll run this in person, is people bring their laptops to school, and we get in groups and we kind of work through this together. And so I'm going to ask you try this yourself. So I'm going to share my screen again. And what we're going to do is look at an activity that allows us to manipulate these two functions and think about which one of these things they're doing. I know I just kind of went through and showed you, but now we're going to actually sort of get our hands dirty and look at that together. So let me go ahead and share my screen again. And you should go to our Blackboard course. And in that course, go to course documents. So here's our Blackboard course. Go to course documents. Down at the bottom, there's a folder that talks about the trig activity, the trig graphing activity, graphing sine and cosine and Desmos. So we're going to go into that folder. And then you just click this link. Right, so it's course documents, graphing sine and cosine and Desmos. And then click the link there. And it'll open up a new page that we can play with. So pause the video if you're not there yet. If you're there, great, let's keep going. So here are the two graphs that are being plotted. Right, so here's the sine graph on the top. It's the red line. And then the black line is the cosine graph. You can turn them on or off by clicking the button on the left side of the screen. So I can click this graph and it turned the black one on or off, or you can click the red one and it'll turn the red one on or off. Right, so let's just play with one at a time. When I turn the red one on, it's sine. You can see it's got the sine shape that starts at 0, goes up to 1, down to 0, and then it does the same thing on the bottom half. Right, so we traced out that sine curve because it's tracing out the y values on the unit circle. Now what's going on the left side of the screen here, you can see with the sliders, is it's plugging in values for A, K, B, and C, right? So A, B, C, and K, you can control via the sliders. And so what we can do is we can change one of them, make it bigger or smaller, and see how it impacts the graph. So A, for example, is the thing that's multiplying the sine and the cosine. And if we drag it and make it bigger, oh, it stretches it vertically. If we drag it the other way, it shrinks it vertically. If we make it negative, right, it's actually going to flip the graph upside down. And so we now have an understanding of what the A does with respect to the sine and the cosine. And we can do the same thing with the cosine. We could turn them both on actually at the same time, and it'll do the same thing to both graphs. I know this is just a little confusing looking because it's like, whoa, there's a lot of lines. But this is just sine and cosine being vertically shrunk or flipped or stretched, depending on how big the A was. We can do a similar thing with B. Let me turn the sine off. Let's just look at cosine. So cosine's got the bowl shape, right? See, if we trace out the first period on the cosine graph, it makes a bowl. If we mess around with the B, let's do that. If we make B bigger, oh, it's shifting it. It's shifting it to the right horizontally, right? It's not getting bigger or smaller vertically. It's just shifting it side to side. And so doing that, we can see that the B shifts it side to side. The C is the thing that's being added outside the function. And when we mess around with the C, you can see it makes it go up and down. And so the C is controlling vertical shifting. And then the K is horizontal shrinking or stretching, depending on how big it is. So this is sort of what you can play around with for a second. And I'm going to switch back to my document camera and give you an opportunity to try it. But let me just, just say that after I remind you or show you how to do this next activity, you should sort of come back here and see what you can make of it. Okay, let me stop presenting so I can go back to my doc cam, because let's look at what it says here. Right, so this is what we just did. We just kind of played around with that thing on Desmos. Keep that open. We'll play with it some more in a second. But what we want to think about, what we're trying to do here is, and what I just did in words, is think about what the A, K, B, and C are doing to those graphs. And we just talked about the types of transformations that each one of those things is doing. And so that's what's being shown right here. So we're trying to get at, what are these things doing to the graph? What are their values in the base function? Okay, if you're kind of following along, I suggest you give that a try based on what you just saw. Again, you can sort of go back and forth and think about, in just regular old sine, regular old cosine, what do A, B, C, and K equal? And then what do each one of those components do in terms of a transformation? Like, what do they do in terms of vertical shifting, stretching, etc.? I'm going to go through that right now, but if you're following along and you understand the unit circle, you're more than capable of doing that. And that's what I usually ask students to do. So pause the video and maybe give that a try. If you want me to give it a try and show you what I mean, I'm happy to do that. So in regular old sine, right? So again, we have these crazy transformations that are going on each one of these things. But if we want, what do we need to plug into A, K, B, and C just to get regular sine and regular cosine? Right? That's what this question is asking us. Well, if I want this function to look like this one, or rather this one to look like this, there's nothing being added to this, right? So the C value would be 0. There's nothing being subtracted from the x, right? The x is just by itself, and so b is also 0. Right? What's multiplying a out in front, right? The a value is the thing multiplying this thing. What's being multiplied right there? Nothing, which means it's just a 1 out front. Right? And lastly, what's multiplying the x? Well, there's just nothing shown there, which means it's also just a 1 multiplying it. And so in these are the values that you need to plug into these functions just to get the regular sine and the regular cosine. And so what I'm trying to say by that is that when we traced out this graph, for example, and made this shape, right, just regular old sine, in terms of transformations, the A was 1, B was 0, C was 0, and K was 1. And so all of these things that we just wrote down, these are what I would call the baseline values. And anytime we change these values, it's going to result in a transformation. Okay, and if you go back to the Desmos page, you'll see that these are the values. You can refresh the page if you need to. These are the values that you start with, because that's what gives us the base function sine and cosine. Okay, and so again, think about, what does a do when you change it? When you change it from 1, let's write that down right here, the component a, what does it do? When you change b and make it something other than 0, so that's the thing being subtracted from x, what does that do? Go through each component and think about what each transformation does. Pause the video. When you're all set, unpause it. I'm going to go through it right now. Well, the a component does two things. It's the thing multiplying sine, so that actually vertically stretches it if it's bigger than 1. It'll shrink it vertically if it's between 0 and 1. And if it becomes negative, it's a vertical flip. Right? So a is in charge of vertical things, specifically stretching or shrinking, or if you make it negative, it'll be a flip. The b is what's being subtracted from the x. Right? And so that's, if you go to the Desmos site, you'll see that that's controlling horizontal shifting. And specifically, it's going to go to the right if you have something that says x minus b, and it's going to go to the left if you have something that says x plus b. So it depends on what the value of whether the b is plus or minus. The c is the part that's being added or subtracted from the function. And if you go to the Desmos site, and we saw that together, that's controlling vertical shifting. Right, so go to the Desmos site and make sure you see that. Right? The c is controlling vertical shifting. And what you should see there while you're playing around with it is that it's going to go up if c is a positive number, or it's going to go down if c is a negative number. Again, we can relate this all back to that function transformation section. That's what we should be thinking about. And then the k is the thing that's multiplying the x. And we saw in the function transformation section, right, multiplying the x is this right here, horizontal stretching or shrinking. In this context, it does several things. So this is going to be a horizontal stretch if it happens to be between 0 and 1. Or you think about that opposite for the horizontal things. Or it's a horizontal shrink if k is bigger than 1. And we also see on the Desmos thing that that's going to be a horizontal flip. It's going to flip horizontally like this if k is a negative number. So when we see something, this sort of complicated looking expression, this a sine kx minus b plus c, a, k, b, and c are doing the transformations. These are the transformations that they're doing. And you should be able to see that in the Desmos site. So with that in mind, we should be able to think about transformations of functions. We should be able to look at graphs and think about transformations. And we can introduce some additional vocabulary as well. Now that we kind of have an understanding of the basic form of a trig transformation, namely those two forms right there, and how each one of those components affects the transformation, we can start to think about some transformations. And so first couple we're going to look at just in words. Again, this is the kind of thing where, if you get what we're doing here and you think you want to give this a try, give it a go. I'll at least show you the first one, and you should definitely feel comfortable trying it by the second one, if not earlier. I want to write the equation of a sine function that's been shifted up 10, left pi, flipped horizontally and stretched by a factor of 2, we apply these transformations to these functions, and it becomes the following. Right, so we're going to mess around with sine. The first thing we're going to do is we're going to vertically stretch it by 2. So that's the a. Vertically stretching is when it's bigger than 1. If we want it to be a factor of 2, that means a is 2. And so we'll have 2 sine. That's going to be the vertical stretch. Flipping horizontally, according to this, is k being negative. And so we'll make k negative 1. If we want to shift to the left pi, that's a horizontal shift, and it's going to be left if we have a plus whatever. And so we want a left pi, and so we want to have a plus pi. And then finally, we want it to go up 10, right? And so up and down is vertical shifting, goes up when it's positive. So I have a plus 10. Right, so dissecting it further, this one's going up 10. This one's going left pi. This is the horizontal flip. And this is the vertical stretch. Hopefully that makes sense. Again, you should definitely feel comfortable trying the second one. It's a very similar kind of thing, except just with cosine. And so give that one a try. Pause the video, and then I'm going to go over it. Okay, so we're going to mess around with cosine. Let me just write down the cosine part. Let's see here. If I'm reading through it, we want it to be shrunk horizontally by a factor of 3, down 2, flipped vertically, right 9. Okay, so flip vertically, the first thing I'm going to add, that's going to be the a value being negative. And so we'll have negative 1 to flip it vertically. We are going to do a horizontal shrink by a factor of 3. And so that's going to be the k, and it's going to be a shrink when it's bigger than 1. So if we want to shrink by a factor of 3, we're going to have a 3 out in front here, multiplying. If we want to go right 9, that's going to be the horizontal shifting, right if it's a negative. So we'll have x minus 9. And then if we want to go down 2, that's going to be the c value being negative. All right, so we've got the vertical flip. We have the horizontal shrinking with the 3. We've got to the right 9, and then down 2. So that's how you could think about a transformation of a function just given words. You know, the flip could also be a question too, right? So I could give you one of these functions and just say, what are the transformations being done, right? So if I wrote that down, you'd say, oh, it's been vertically flipped, shrunk horizontally, right 9, down 2. Okay. All right, now that we kind of have an idea of that, let's learn a little bit more vocab and then dissect this a little bit further. So when I was going over the sort of some of the applications, I talked about how the different size of the wavelengths oftentimes mean different things in the application. For example, how big or small it is depends on whether or not you can see it, right? We talked about that. And so some of those specific words deserve their own definition, and we oftentimes talk about those words when we're looking at a graph. And so these words particularly, amplitude, period, and the phase shift. So the amplitude talks about the peak of the graph, and so that you can see, and there's a picture down here sort of describing it, right? So the amplitude is the height of one of the peaks. In other words, it's half the distance between the biggest and the smallest piece. So if you're looking at this graph right here, the height of it is this entire piece, but the amplitude is just half of it, right? So it's kind of like the height of one of the peaks is the amplitude. So you could look at a graph and just sort of figure out what the amplitude is, or notice that it's also given by the value of a, right? Because a does the vertical stretching or shrinking, and so that's going to determine the size of the peaks. And so the a part of those graphs tells us the amplitude. The period is how long it takes the function to repeat itself, right? We wrote down that definition down early on. And so how long it takes to repeat itself depends on how wide the graph is, right? So if we want to know how wide the graph is, that's why it depends on k, right? So you can see that the k value is part of the period function, right? So normally it's 2 pi, but you divide by k to determine if there's been any stretching or shrinking horizontally. And then the phase shift is any shift left or right. So if we go sort of left or right with the graph, that's just called a phase shift, a horizontal shift in the graph, b units. And so that's why the b controls the phase shift, because that's going to shift the graph left or right. We said that on the last page, right? And so you can just sort of see that in the picture here. And then very obvious questions that go along with that are, you're either given a graph, right, like this right here, and asked what the period, phase shift, etc. are, or you could be given a picture like the bottom here, and just looking at the picture, we should be able to figure out those things as well. Again, if that makes sense, maybe give those a try. If not, I'll go through them right now. Okay. So hopefully you thought about that at least a little bit. Maybe at least you could think about this one and the picture. First one people get a little bit confused by sometimes. So we're going to determine the amplitude, period, and phase shift of just the normal sine and cosine graph. So, we had said previously in this graph, A is 1, B is 0, C is 0, and K is 1. And so if that's the case, then we should be able to plug them into these formulas and figure out each one of those values, right? So this is the normal sine / cosine graph. And we had said in that normal sine cosine graph, if you look on the previous page, we had said that A was 1, B was 0, C was 0, K was 1. Right? So these are sort of the baseline values that we think about. And so what does that result in terms of amplitude? I'm going to get out my original picture here and just we can reference that as well. Right, so the amplitude is the absolute value of whatever A is. In this case, A was 1. And so A is 1. And so that means the absolute value of 1 is 1. And we see that in the graph. Right, this is the first page of sine. Right, so here's the sine graph. The amplitude is the height of one of those peaks. The height of this peak between my two pens right now is a height of 1. Right, so this is a height of 1. That's why we ended up with an amplitude of 1 in this graph. The period of a normal sine or cosine graph, you do 2 pi divided by k. In this particular situation, k is 1. And so we'll have 2 pi divided by 1, which is just 2 pi. And we know that. We already knew that, right? We knew that the period of a normal sine or cosine graph is 2 pi. Again, if I put up this original picture, this was one period, right? We said this is one period of sine. That went from 0 to 2 pi. That's exactly what that says right there as well. Phase shift. Well, none of the original graphs aren't shifted at all. That's the baseline. And so in this case, B is 0. And so the phase shift is just 0 in this case. Right? In other words, these things start at 0. They're not shifted away from that. Any shift away from that is going to be a phase shift. And then finally, what's the interval, the entire interval, right? So it goes from B to B plus 2 pi over k. In other words, the B controls the shift, so it shifts over, and then the k controls the horizontal stretching or shrinking. And so when we look at the entire period of the interval, it starts at B, and then k controls where it ends. In this particular case, our B is 0 and our k is 1. And so it's going to go from 0 is B to 0 plus 2 pi over 1. Right? 0 plus 2 pi is 2 pi. And we already knew that too, right? The interval that the normal sine or cosine graph goes from 0 to 2 pi. Again, back to the original graph. So let me look at both of them together. Sine goes from 0 to 2 pi. That's one period. Cosine goes from 0 to 2 pi. One period. And so this is just sort of relating what we already knew, the amplitude and the phase shift and the period of these things, back to that picture and looking at it in terms of the formulas for A, B, C, and K. Let's look at one that's now transformed, right? So here's a transformation that's being done on sine. We can write down what a, b, c, and k are here and plug them into the formulas to figure out the new values. Right, so if I'm looking at this function right here, a, oops, sorry, dropped my pen. A is the number multiplying out front, and so a is -3. Right, b is the number that's being subtracted from x, so b is pi. C is the number that's being added or subtracted, so C is the 2. And K is the number that's multiplying the X, and so K is 4. So this transformation, a bunch of things are going on there, but these things are describing what they do, and we can figure out the amplitude, etc., using those values. So if we want to know the amplitude, we take the absolute value of A. And so the absolute value of A in this case is the absolute value of -3, which is 3. And so this graph has been stretched by a factor of 3, right? It's been like stretched vertically. And so it's going to have a higher amplitude than the base case, which just had 1. The period is 2 pi over k. In this case, k is 4. And so we'll have 2 pi over 4. That reduces to pi over 2. Right, so this one has been shrunk horizontally, and so it has a smaller period. It's also been shifted, right? The phase shift on this b was pi, and so the phase shift is going to be the b value, which is pi. In other words, it went to the pi. It went pi units to the right, because b is pi. And then the interval depends on both b and k. So we said b was pi, k was 4, and so the interval is going to be pi. I got shifted over by pi, and then we do pi plus 2 pi over k, which is 4. Right, so pi to pi plus pi over 2. That's going to be pi to 3 pi over 2. So given some equations like these, we can pick out the amplitude, period, phase shift, and period interval, without even looking at a graph. But we could also do the similar thing given a graph. Right, so here's a graph. This looks like a cosine function. It looks like a cosine because if I just cover up half of it, it's got the bowl shape. Right, it's got the bowl shape over here too. So it definitely looks like a cosine transformation. And we can figure out the amplitude, period, and phase shift as well just by looking at the graph, right? So let's just slide up here and remind ourselves. Period is how long it takes the graph to repeat itself. And so if we go down here, 1 period would be, say, from right here to right here. Right? This is the size of 1 period. Oops, can't really see that, sorry. Right, this is also 1 period. Right, each one of those bowl-shaped things is 1 period. And so that would be the length of 1 period. The amplitude is like half of the entire graph, the height-wise, right? So the amplitude is half of that. And so if I'm looking at this one, the entire thing is from here to here. And so half of that would be an amplitude. And so that distance is the size of 1 amplitude. And basically that's all we need to know, right? We'll look at the phase shift when we get to that question, right? So let's look at the amplitude. The amplitude is from right here, halfway across, to right there at the end. That distance from 1 to 3 is a distance of 2. And the distance is the same as the other half, right? The distance from 1 to -1 is also 2. And so the amplitude is from 1 to 3, or from -1 to 1. And so that means the amplitude here is a distance of 2. We've marked out the period. The period starts at 0, goes to pi over 2. That's a distance of pi over 2. So the period of this thing has size pi over 2. Phase shift is whether or not it's shifted left or right. Well, cosine usually starts at 0, and this one still starts at 0. Right, if I put up my base function for cosine again, it hasn't shifted away from this, right? It hasn't shifted left or right. If there was a phase shift, this starting point would be off the y-axis. And so, just to be clear, I'll draw this one. Normal cosine looks like this. Starts at 0, and this one still starts at 0. And so this one has no phase shift. And the period interval is just where it starts to where it ends, right? So it starts right here at 0, and it ends right here at pi over 2. And so one period could be from 0 to pi over 2. Again, because this is where it starts. One period starts, and that's where it ends. You might see questions like, similar to these in the homework, trying to go over different types you might see. The last kind of thing you might see in a homework looks like this, where you're just given some basic transformations and you want to match it up to graphs. Right? So here are a bunch of sine transformations. We're going to figure out which transformation is going on, like what the transformation is being done, and we'll match it up with one of the graphs that's at the bottom of the page there, or right below it, I mean. In order to do this, it would be really helpful to know the base function for sine. So let me just slide my paper down, and I'll just draw it right at the top here. So normal sine from the first page, we know starts at here, has like the top hump, and then has the bottom hump. So that's a normal sine function. It goes from 0 to 2 pi. Excuse me. And it usually goes between -1 and 1. Okay, that's a normal sine function. Anything that deviates from that is a transformation. So we know that if there's a t plus 2 inside there, I'll grab my last page to put it back up here. This is horizontal shifting, right? The k part is horizontal, excuse me, the b is horizontal shifting, and it's going to go right if it's a minus, and it's going to go left if it's a plus. So we've got a plus 2, and so this plus 2 is going to the left too. Okay, and then we should be able to, based on this normal graph, we should be able to match it up with the one that it is. Take a second and try that. Right? So go through each one, figure out what transformation is being done, and try to match them up. Just pause the video and give that a go. This is how we learn, by the way. You know, if you're not doing this stuff, I can't force you to, of course, but this is your opportunity to learn, make your brain grow a little bit. So if we want to make this graph go left 2, right, then it's not going to start at 0 anymore, this graph. It'll start at -2. The one that seems to be starting at -2 is this one right here, right? And so let's label this graph D. Well, this one is associated with that because it went left 2. This one is multiplying the t by 2. So the t, in other words, the k is 2. And so this is like a k equals 2 situation. And so that's a horizontal shrink by 2. So we're going to look for the same graph, but instead of going from 0 to 2 pi, it's going to be shrunk in. So it'll go from 0 to pi. Right? And so that would be this first one. Right? Instead of going all the way to 2 pi, that single shape is crammed between 0 and pi, right? This shape has been shrunk down and it's now smaller. This one right here has an a value of 2, and so we're stretching vertically by 2. So the same graph, but instead of going between -1 and 1, it's been grabbed and stretched out. And so it should be going between -2 and 2. Well, that's this graph, right? Graph C. And lastly, by process elimination, we can see that this is B. Let's just figure out why it's B, right? So in this graph, C is 2. And so that means it's going up 2. And the one that's going up 2 compared to this would be this graph right there. Okay. So those are how we basic transformations work with respect to sine and cosine. At the bottom of this page here, it's just another reference. I had some extra room, and so I thought I'd put a reference for horizontal motion because sometimes people get confused by that. And so this is just kind of showing the normal sine function, right? So the black line in the middle is sine going between 0 and 2 pi. And then it's showing that when the k is 2, it gets shrunk down half as much. This is showing when k is 1/2, how it gets spread out. And when k is 1/3, it gets spread out even further, right? So it's showing horizontal stretching and shrinking, right? It's not getting bigger and smaller at all. It's all the same height. It's stretching or shrinking side to side. Similarly, this is horizontal shifting. And so it's just showing us b being minus pi over 3 or b being plus pi over 6, right? And we can see that it sends a graph side to side. That's a good reference for that, right? Horizontal stretching and shrinking follows horizontal transformations, obviously, which, as I explained in our previous video, is counterintuitive to the way that we usually try to think about that. And we went through some exercises about how to think about that. Those apply here as well. Please let me know if you have some questions. I know this can be a tricky section. Try to look at this as soon as you can. And let's get together in class and talk about some of it.